Welcome to HurricaneCenterLive.com. I'm Alex Garcia, Director of the National Tropical Weather Conference and Executive Producer of these programs. These programs are made possible by USAA, the South Padre Island Convention and Tourist Bureau, and Plylux Hurricane Clips. These programs are also a team. And Tim Smith will not be able to join us today, but we do have everyone else here. It's going to be an exciting program. We're going to turn it right over to Bill Reed. So, Bill, take it away.
Good morning, everybody. As usual, we'll start off with a overview of what's going on in the tropics around the world today, and it's kind of busy, to say the least. This is a current satellite loop showing the Atlantic Basin and into the Eastern Pacific. Nothing of consequence at this time in the Eastern Pacific. We have our two storms, Sam and Victor. We'll talk a little bit about each of them. Caribbean's for this time of year is virtually quiet, and a cluster of thunderstorms on the Texas coast that is tropical moisture, but it's being activated by a disturbance, a weak disturbance in the westerlies coming out of northern Mexico and the southwest U.S. Not a potential for development at this time. And here is the current outlook. You see no other areas of interest on the outlook there, so we'll go right to Hurricane Sam. I'll try Wondergrounds mapping of that to show the long history of Sam. It formed on the 22nd out in the deep tropics. Has been moving much slower than is typical in that part of the basin. Went through some rapid intensification over the weekend, and is still a very intense Category 4 hurricane at 130 knots this morning. Moving north, is passing. It will be passing just to the east of Bermuda, and in spite of the long track and lots of intensity, other than the wave action and dangerous hazards for surfers and any ships that decide to get in the way of this thing, it's not going to impact land areas, and it'll become a very large and powerful extratropical storm by early next week east of Atlantic Canada. As for Victor, it formed yesterday, I believe. Again, in the same general area in the deep tropics. It's intensified to now a 55-knot tropical storm, and I haven't had a chance to look at the latest advisory, but the general thinking is that it's going to reach its peak here in the next 12 to 24 hours, and then go through a weakening trend as it goes into a much more hostile environment than Sam had, with encountering a lot of dry air and eventually a lot of wind shear. And not be much of a threat, again, out in the open ocean throughout its lifetime. Elsewhere in the globe, we have Mindul, Typhoon Mindul, which has had a very similar history to our Sam. It's very interesting to follow the parallels in that it's in the process of transitioning into a large extratropical cyclone, which will be in the Bering Sea this weekend, or early next week. And again, here was the formation, again, the deep tropics, went through a rapid intensification as it was recurving, and towards the mid-latitudes, stayed a significant Category 4 typhoon as it moved slowly to the north and then began accelerating yesterday. And again, the threats are high seas and beach erosion and the like in the country of Japan. One more area of interest this morning. This is Cyclone Gulab, which is intensifying over the very northern Indian Ocean, heading towards the Gulf of Oman, paralleling the coast of Pakistan, Iran. Very rare to get there's not that many tracks in the history books on storms that make hurricane intensity. It is forecast to become a hurricane strength storm before making landfall in northern Oman and have an impact on the United Arab Emirates and Dubai later this weekend, early next week. Probably bring more rain than you'll see in a typical year. moving slowly like is indicated in the forecast there. So that's it for the tropics now. I think we'll pause here for a sponsor break, and we'll be right back with today's speaker.
The National Tropical Weather Conference and NTWC-Live are brought to you by USAA, the South Padre Island Convention and Economic Corporation, and Plylax Hurricane Clips. Additionally, we have support from Maglite and from Blackmagic Design. All of these corporations and companies help keep the National Tropical Weather Conference and NTWC-Live going for you throughout the hurricane season. And we'll be here throughout the day. And, of course, throughout the season. We're also going to be having our national conference coming up in April. We're planning an in-person conference, and all of these companies are helping us to produce that as well. Thank you so much for joining us, and we'll turn it back over to Bill Ree.
Interesting choice for a speaker today, somewhat out of our geography of the hurricane belt, but Dr. Chris Funk is an internationally renowned expert on climate extremes, early warning systems, and climate change. He is the director of the University of California, Santa Barbara's Climate Hazard Center. The center is very instrumental in trying to develop knowledge systems that can allow people to better prepare for the extremes that come up with climate. He's a very prolific writer with over 190 publications, but of interest today is his book writing. He's on his third book. It's just been released, and that's what we're going to talk about today is a Cambridge Press book, Drought, Flood, Fire, How Climate Change Contributes to Catastrophes. So, Chris, take it away.
Okay, yeah, thanks a lot, Bill. Okay, well, thanks for that great introduction, Bill. And I just want to say I'm really honored by the chance to speak with your community, and the work that you're doing obviously is really important. And, you know, I think one of the things that this book and the talk today can kind of bring to you is, you know, pulling back and, you know, thinking about the work that we all do in kind of a big perspective. I'm the director of the Climate Hazard Center, which is at the University of California, Santa Barbara. I work with a team of international scientists in Africa and Central America, and then programmers and scientists and students at the university. We're primarily funded by the U.S. Agency for International Development's STEM and Early Warning System Network. But during the government shutdown in 2018, I had time to kind of pull together a side project, which was kind of a synoptic overview of drought, flood, and fire, how climate change contributes to catastrophes, which with the help of my editor, Matt Lloyd, and Diana Rossetto at Cambridge University Press, is a book that basically covers the basics of climate science, and then, you know, the different categories of extremes, and discusses how climate change contributes to those. And, you know, I'm an operational person. I kind of bridge the research community and, you know, kind of operational early warning. And so I just thought I might start this just with a little, you know, introduction to some things that I'm doing right now to kind of let you know where I'm coming from. So, you know, at 7 this morning, I was on a call with the United Nations talking about predictive analytics in the Sahel, West Africa. This afternoon, I'm going to be talking with a Canadian Climate Disaster Project collaboration. That's a group of students and reporters and researchers who are discussing how to discuss climate in the context of outreach. On Monday, we have a paper, Global Urban Population Exposure to Extreme Heat, coming out in the prestigious Proceedings of the National Academy of Science. The same data is discussed in chapter 5 of my book. And basically, it's a data set that we produced here that's kind of the best possible data set, especially in areas that don't have a lot of observations of temperature. And it shows that essentially heat exposure is increasing much more rapidly than we thought. Later in October, in the next issue of the Bulletin of the American Meteorological Society, I'll be leading a paper on an excellently graded precipitation data set. I'm basically a precipitation scientist. I work closely with NASA. Then there's this discussion, which is going to talk about hurricanes, cyclones, and typhoons, and conceptual models of climate change and prediction, and how those two things relate. Doing a lot of work forecasting East African droughts for 2021-22, and we'll talk about how we think about climate change can inform our ability to predict. And then finally, I'm also, this week, I've been working with the U.S. Drought Monitor to improve forecasts of rangeland fodder and fire fuels. So even though Drought, Flood, Fire, is a book that you should sit down and read, it was written in the context of my work, which is kind of really close to the front lines, like I think a lot of people on this call are. So, one of the things I get paid to think about is early warning and how we can make early warning better. And, one of the things I've realized in about 20 years in this business is that conceptual models matter. So the sort of earliest early warning systems, were these radar systems that the British were using to try to anticipate bombers coming in from Germany, right? And, the search patterns that you have when you're trying to analyze signals really make a big difference. And early warning systems depend on those. And I'm going to talk today about how an energy convergence conceptual model can inform prediction. If we want to look for trouble, we should look at where the energy is going. And nothing is more exciting, of course, in that context than extreme tropical weather. This energy convergence model can help link climate change and climate extremes. Essentially, instead of thinking about climate change as this sort of average of a bunch of climate simulations, we need to think about it as something that's increasing the energy in the ocean and in the atmosphere, giving us opportunities to monitor and predict. So energy is building up really quickly in our oceans. And here I'll just quote from my book. The energy stored in the ocean accounts for about 93% of the total increase in the climate system since 1971. Figure 8.1 shows a time series describing the total amount of energy in the top 700 meters of the world ocean, expressed as anomalies. It took us about 30 years to go from an anomaly of -3 times 10 to the 22nd joules in the 1960s to about +3 times 10 to the 22nd joules in the late 1990s. The current anomaly is more than 5 times this amount. Between 2014 and 2021, we see another +5 times 10 to the 22nd joule jump. A +5 times 10 to the 22nd joule increase in energy is equivalent to the energy released by about 12 million 1 megaton nuclear bombs. So, sorry, there's a lot of 10 to the 22nds there. But the point is that, in the ocean, the energy is building up very rapidly as it's accumulated due to greenhouse gases. And, even in the last, 5 to 6 years, we've seen this big jump between the early 2010s and 2021. So that energy is going into the ocean, but it's not staying put, right? It's moving around. And so here I'm showing an animation of NASA combined land sea temperatures expressed as standardized anomalies. Anything red is exceptionally warm, and each individual image is a month. And, the point is that this, energy moves around. And of course, the ocean is related to extreme tropical precipitation. And over land, we can have heat waves, increased fire risk, et cetera. And, all of this is associated with the movement of energy, which we can track using satellites and computer models. If we just focus on the change in the area of the Earth that has been extremely warm, I've just measured this by looking at the area in each month that has standardized temperatures greater than plus 1.5 standardized anomalies, right? So it's kind of on the far right-hand side of the bell curve. And in the late 2000s, it might have been about 8% of the Earth's surface. But in the last 5 or 6 years, we've seen that jump up to about 25%. So we've seen a really rapid increase just in the last decade of the amount of the Earth's surface that is exceptionally warm at any point in time. And so we're going to talk today about how that warmth it can affect both extreme precipitation and droughts and fires. So here's an example that I've been doing this week for the Famine Early Warning System Network, trying to prevent famine in Africa. This is kind of what I do for my day job. Last year, at this time, I was publishing a worldview piece in Nature saying that according to my forecasts, I thought Ethiopia, Somalia, and Kenya were going to face devastating droughts. Those droughts happened in October, November, December of 2020, and March, April, May of this year. And now the region faces really extreme food insecurity. Of course, there are other factors as well, poverty, conflict, prices. But, we were able to predict these droughts very, very far in advance. And, just today we're putting out alerts talking about yet another drought in March, April, May of this year. And so if we look at the forecast for March, April, May of 2022 from the most recent data, we see exceptionally warm sea surface temperatures in this kind of Western V region. And when we look at both forecasts and observations of those temperatures, we see that they stratify dry March, April, May, East Africa rainy seasons really well. These are these orange circles. So this is forming the basis of anticipatory action that is being done by the United Nations, by the Famine Early Warning System. And so by paying attention to where we're finding exceptionally warm conditions in the atmosphere and the ocean, we can improve our predictive capacity. And another way to improve our predictive capacity is to use staged early warning systems, or take a defense in depth kind of approach. So, if we have a castle, we have a moat, and we have, the walls of our castle, then we have an inner keep, and cybersecurity experts and early warning experts advocate these kinds of approaches because they give us multiple chances to be prepared. And so, in the context of hurricanes and cyclones, way before the season, we can use our insights about climate extremes and climate change to develop better weather models, develop and provide seasonal outlooks. Then as the season progresses, we can track the drivers. Where are we seeing very warm sea surface temperatures? Where do we see elevated convectively available potential energy, et cetera? And of course, we can predict and monitor. And we know that a warmer atmosphere produces more intense hurricane precipitation. We'll talk about that. Some people like Jim Cosin is doing some really interesting work suggesting that hurricanes seem to be traveling slower. So kind of a priori, we know that when we see a cyclone in today's climate, we might have more reasons to be concerned about it. And I think your community is doing an excellent job of communicating those risks. So which type of disasters are the most expensive? One of the neat things about doing drought, flood, and fire book was that I could pull back and kind of survey the landscape and look across the different types of hazards. And if we just look at what happened in the US in 2020, this will help us pretty much recognize that extreme precipitation and cyclones are the most damaging. So this is based on the NOAA billion-dollar disaster database. The number of US billion-dollar disasters in 2020 was 22, the most on record. 7 of those billion-dollar disasters were tropical cyclones that struck the US. So extreme tropical weather is a really big ticket item. We can use this database to just make a time series of both the number of billion-dollar disasters and their costs. The total cost, according to this data for 2020, was $170 billion. So these are having huge impacts. And as you can see, the magnitude of those impacts is going up over time. We're not sure how much, the Hurricane Ida will cost. Estimates seem to be around $90 billion. So I've sort of pasted it in there on the right. But there's a clear tendency towards, more costly disasters. And, a big driver of this is economic growth, right? Not all weather and climate, but that's certainly playing a role as well. Another source that we can look at, and I look at this in my book, is this EMDAT International Disaster Database. So this kind of lets us look all over the world. And, what you see, this is just the disasters of the week there on the right. Floods, severe weather floods, right? Extreme precipitation, cyclones, are really disastrous. And if we just query this database for 2015 to 2021 flood and storm impacts, we found about 3,000 events impacting more than 500 million people, and costing about $900 billion. Sorry. So these are really huge costs. Another source that we can go to is reinsurance databases and reinsurance data documents. So reinsurance companies, and so they track the cost of these extremes very closely. And according to Aon Benfield's annual report, the most widespread and newsworthy events in 2020 were recorded in the United States during the record-setting Atlantic hurricane season with 30 named storms, 13 hurricanes, and 6 major hurricanes. I know that this community realizes how extreme 2020 was. It was just very, very costly. And a big part of the cost, interestingly enough, was severe convective storms. That was actually even more expensive than the cyclone impacts. So these are very dangerous events. So, I try to kind of boil down a lot of the take-home points in the book. So here's 5 things that we all should know. First, the Earth is getting a lot hotter very quickly. And, even though I'm a climate hazard scientist, when I did the work to do this book, I was really shocked at how, if you look across all the different data sets, the speed of warming and the speed of increases in extremes is very, very rapid. And just over the last decade, things have gotten a lot hotter, and there's a big increase in a lot of extremes. Another thing to know is that the atmosphere is really thin. It looks huge, but it's really not that thick. And that means that, a relatively modest amount of greenhouse gases are really changing things rapidly. And it also means that warming increases the atmosphere ability to hold water. And this very simple principle can lead to more extreme precipitation and more severe droughts and more extensive wildfires. And, I think the broadcast community, can help us communicate to the regular public, this relatively simple idea, which lets everybody understand, a major portion of how climate change is increasing severe precipitation, severe droughts, and more extensive wildfires. So we'll dwell on that a little bit. And then, and this creates more hazards like extreme tropical weather. So, those last 2 bullets, I think, are 2 simple but really important ways to think about how climate change is modifying our weather. So I like this picture taken by Scott Kelly from the International Space Station, just showing how thin our atmosphere is. We can think about this in the context of Hurricane Ida. Looking at it from above, we see it spanning, hundreds and hundreds of kilometers. But if we look at animation, we can't find a file. Oops. If we could do the animation, sorry, we would see a zoom in to Hurricane Ida, and we would see the transect of the diabatic forcing, and it's only about 10 kilometers deep. So, when we look up, the universe looks vast, or the atmosphere looks vast, but when we zoom in, it's only at 10 to 15 kilometers is where most of the stuff happens. Sorry about that broken link. So here's another kind of view about it. We have a schematic of a cyclone. It's about 15 kilometers from the surface to the tropopause. And, cyclones are really amazing systems because they are associated with the convergence of incredible amounts of energy, right? So hundreds of kilometers, evaporation, a huge fetch from the ocean can all get drawn in to a cyclone, triggering really extreme precipitation. And a good example of that is Harvey. In 2018, Harvey brought 9 trillion gallons of rain to the Houston area. The total energy associated with evaporating 9 billion gallons of water is about 76 times 10 to the 18 joules. In 2017, the humans around the world consumed about 630 quintillion joules of energy, or just 8.3 times the amount of energy released in Texas by Hurricane Harvey. So, in a very, very limited area, and perhaps a day or a day and a half, right, you had this incredible amount of energy released as precipitation. And so if hazards are associated with the convergence of energy, extreme tropical weather is, the most marked example of that. So, just some simple cartoons that we all know. And I'm not really presenting this. I don't think this community is going to learn this for the first time, but I think it's useful to talk about how we talk about climate change. And so please don't think that I'm being simplistic. So we know that the air is made up of mostly nitrogen and oxygen, and that as the air warms, those molecules move further apart. And so at a given fixed relative humidity, the warmer air will hold more water vapor. And this can be described by the Clausius-Clapeyron relationship, which says that about 7% increase in water vapor for every degree Celsius. Very simple, thing to believe here. It's just basic atmospheric physics and chemistry. But this really simple principle really explains a lot of what we're seeing. So out here in California, where I live, we have yet another epic wildfire year. And a huge part of that is the effect that warmer temperatures play in drying out the vegetation. So as air warms, you have increased vapor pressure deficits, which increase dead fuel moisture, which allow fires to grow much more explosively. And this is really a very straightforward mechanism. But the same simple principle, warmer air holding more water can increase the frequency of intense flood events. So, cold air rises, reaches a lifting condensation level, precipitation happens, and we get precipitation and rain, right? If the external conditions are all the same, but the air is warmer, then you're going to get more precipitation. And again, at about 7% per degree Celsius. So this is really simple, but it's also very robust. And, we find really strong evidence for extreme precipitation increasing in observational data sets, and reanalyses, and climate model simulations. And so this is one part of the puzzle that seems, really quite solid and certain and backed up by all the evidence that we have. So I'm certainly not a tropical cyclone expert, but I do chair sessions at the American Geophysical Union where, I've had a lot of the distinguished experts speak. And, I can just report back from this WMO task force synthesis conclusions on climate change and cyclones. I think some of these speakers have probably been with you in the past. But they find that there has been a detectable increase in the global proportion of tropical cyclones reaching category 4 or 5 intensity in recent decades, and anthropogenic forcing has contributed to this increase. I'm just quoting from this paper. There has been a detectable increase in the global average intensity of the strongest tropical cyclones since the early 1980s, and anthropogenic forcing has contributed to this increase of global average intensity. there has been a detectable long-term increase in the occurrence of Hurricane Harvey-like extreme precipitation events in the Texas region, and anthropogenic forcing has contributed to the increased frequency of Hurricane Harvey-like precipitation events in the Texas region, and there has not been a detectable long-term increase in the global major hurricane landfall frequency in recent decades. So when I read this paper and listen to these talks and think about how these findings are similar to what we're seeing in the drought world, in which I'm quite an expert, and the fire extremes, and I think what we see is that the strongest evidence for climate change is relating to the simplest things. So if you think just about fires and extreme tropical weather, they're both extremely complex. Fire ignition and fire weather is extremely complex and nonlinear, just as tropical extreme weather initiation, amplification, and propagation can be extremely complex. And the whole gamut of hazards, these things, are the most difficult to model and predict. And, we find relatively little evidence for changes in fire and cyclone frequency. But once these, extremes get going, fired up, fires and extreme tropical weathers face serious energy constraints. So we find robust evidence for increases in magnitude, bigger fires and bigger extreme precipitation events. So, when we have an extreme precipitation system going on, this Clausius claparound kicks in, and if the atmosphere is warmer, and it often will be, it's just going to have more water vapor, and we can get more extreme precipitation, which of course is also latent heating, which can, amplify the system as well. And then in the Western United States, it's really complicated about when a fire gets started, whether there's just going to be the right kind of weather that day to have it, grow. But once that, system reaches a certain tipping point, then there's a really, really straightforward relationship between warmer air temperatures, lower dead fuel moisture. That's just the amount of water in sticks and leaves, and warmer temperatures. And so there's very strong evidence that we're seeing, bigger fires all over the world. So, one of the things on the right-hand side, these kind of simple effects, is support for this comes from the fact that bigger fires and more extreme precipitation events are arising almost everywhere feasible. So, we're seeing extreme precipitation in almost every country. We're certainly seeing it in many, many countries in the tropics. And again, we're seeing bigger fires all over, in Australia, in Turkey, in Greece, in Russia. And so, this is a good hint that what we're seeing is, something scientific that is influencing things all over the world in a relatively simple way. So I wanted to quickly share just one slide on extreme event attribution and projection. Extreme event attribution evaluates the contribution of, two slides, of climate change to an individual event by contrasting with counterfactual simulations. This framework can be used to project the influence of future warming. And we do this by starting using a computer model to recreate an extreme event. Then we create pre-industrial simulations to simulate the event in a world with cooler oceans and a cooler atmosphere. And we can also do future simulations that simulate the event in a world with cooler oceans and a cooler atmosphere. So this is a paper in Nature by Patricola and Wiener, where they did a formal attribution study of these three cyclones, Katrina, Irma, and Maria. And on the left, they contrasted two sets of war simulations, one with the observed climate forcing, and then one set of simulations with pre-industrial forcings where things were cooled. And they basically found that, yes, climate change had increased the intensity of the precipitation of these hurricanes in a substantial way. Then they took those systems and they projected out what they might look like at the end of the 21st century if we continue rapid emissions. And they found really big increases in the expected precipitation in these systems, if climate change goes on unabated to the end of the century. So this is, I think, really important science. And, in the last 10 years, our ability to attribute formally the impact of climate change has really increased tremendously. So we're going to have just a few slides to kind of bring it to a close, to talk about why be hopeful. And, I think we're all engaged in the business of hope, right? We're engaged in the business of trying to anticipate extremes and communicate the risks associated with those. This is a picture of my friend Carol, who's digging out homes after a terrible flood hit close to where I live in Santa Barbara. And we can develop interlocking humanitarian networks that share information, support early action, and manage risk. And we're doing this. And I think it's really exciting to be part of that. And we can care for each other in these overlapping communities that can transform data into information, knowledge, and wise action. So, on the left, we have satellites and climate models. And in the middle, we have groups like the Climate Hazard Center, where we can translate those raw, satellite thermal infrared observations into precipitation estimates, into precipitation forecasts, into crop model assessments, flooding assessments that can, lead into early warning systems, and that then go the last mile to trigger wise actions. And, the broadcast meteorology community is really central in this transformation of kind of raw scientific data into, life-saving and business-saving information. I'm also hopeful because the cost of disasters is increasing very, very rapidly. Basically, according to Aon Benefield's data, and again, these are people in the business of risk, not, they're not like a bunch of hippies. They're finding about a doubling or more in the cost since the early 2000s to 2020. And, in terms of climate change mitigation, this should be motivating us to get serious about tackling climate change, because the cost of dealing with weather risks is increasing very, very quickly, and starting to approach the cost of actually just dealing with climate change. And I think we should be hopeful because our ability to perceive climate change is rapidly improving. So in the book, I talk about the renaissance and how in the space of about 40 years, our ability to perceive the human form was radically transformed. And this ability to see nature better and better and better, just continues. And we can now, using the latest satellites, see in great detail. We can feed that information into our weather models and do things like forecast Ida, right? So Ida was a really dangerous and extreme hurricane, but it was predicted extremely well. And so we're seeing huge advances in our ability to monitor and anticipate extremes. Here's just a quote from my friend Scott Braun, and our ability to see, the wind speed, the diabatic forcing, all the details of extreme tropical precipitation is really improved greatly in the last 10 to 20 years. So to kind of pull that together, we should be hopeful because we can care for each other. We can develop interlocking humanitarian networks that share information, support early action, and manage risk. The magnitude of climate losses is rapidly approaching the cost of addressing climate change. But our ability to perceive climate change is rapidly improving, and this perspective empowers prediction. And that's it. Thank you for this opportunity. Oh, Bill, I think you're still muted.
All right, let me give a quick plug to one of our sponsors, and then I'll be right back with some questions for Chris. Um, Fly locks. As you look at the pictures of the damage from Ida over in Louisiana, you see a lot of buildings with windows blown out. Fly locks window clips are made for ease of use to protect your windows during a hurricane. They install in seconds without nails, screws, or adhesives. They're an inexpensive, non-destructive way to protect your windows from high winds and blown debris. Lock in your protection with fly locks. Wow, that was a lot to cover there, Chris, and fascinating information in there. I think I want to ask one question because it was part of the end of what you had before I forget what I was wanting to ask you about. The science of extreme event attribution. I know it focuses on the climate change part of it, but I get questioned a lot when I show the studies that people have done on Harvey on the attribution to the percentage of it that may be attributed to the climate change. Can we use the same concept for giving attribution to, say, the stalling or slow nature of the hurricane, an example of Harvey?
Yeah, I think you had Jim Cosin, I think, talk recently on your show, I believe. Right. Yeah, he's a fantastic scientist and the real expert on this. I think I did review that, the WMO task force report, and I think at this point it's very strong in the data. You definitely see it, but I think that in general, the community is not comfortable at this time, really formally attributing it to climate change. Some people might be, right? Jim may be, but I think when I read their consensus stuff, that's not jumping out as a real slam dunk.
Yeah, here in Texas, that'd be tough here in Texas because the storms generally are slow moving anyway. They're coming across Texas. They're exiting the big subtropical high, and the average speed at landfall is somewhere around 10 miles an hour. So the 10% reduction would be 1 mile an hour. I'm not sure you could milk much from that data to tell you much. In fact, the common thinking is that looking back historically, that the stalling of the storms is probably the principal driver of the extreme rains we get. And that's the way I explain it. And that the warming of the oceans has changed the fuel from regular to premium.
That's a great way to describe it. Yeah, for sure. And I think, with the stalling, the part of the hesitation, and again, I'm kind of just giving you my impression of the community, is that it's just the mechanisms driving it are not so well understood. Mm-hmm. And so, at least for me, my approach to attribution is very diagnostic. I like to understand more the why of it. And so, I spend a lot of time looking at extreme climate and weather, and I like to get into the guts and say, okay, what made this extreme? Like you're talking about. So it's a combination of a slower moving storm plus more, water vapor. And, so I think, so for the stalling, it's obviously very concerning, but I think it's just, poorly understood. And, I had that one slide where I kind of talked about the simplest parts of climate change, right? And that would be the going to premium fuel. Mm-hmm. And I think the stalling is there on the left-hand side of the slide where it's complicated and hard to understand.
Yeah. And I really like your descriptions of the escalation and the damage and the correlation of that, that both growth and a change in the frequency and strength of the hazards that are causing the damage are in there, so people can understand that we keep our practice of building in harm's way, the outcome is not good.
That's right. It's a huge part of the driver. But it's also part of the solution. Like, in a sense, the costs of these extremes are going up because we're getting wealthier, right? We can afford to keep building on the coast. And that also means that we can afford to tackle climate change. I mean, the economy is going up. We just making globally a huge amount of money, and it's about less than 1% of the global economy to really tackle climate change in a serious way.
Mm-hmm. Yeah, I've seen a lot of just in the last few years. I've seen a lot of development at, say, university levels to have institutes that look at mitigation resilience as related to climate change and other things that didn't exist in the past. I like the fact that you really get into the data, and in your book, you're reviewing the latest data available. What are the surprises that come out in the data that you've seen so far?
Well, I think, yeah, I mean, so first, I am by training, I'm a precipitation scientist. I've done remote sensing, satellite estimation, and that, but I focused really primarily on droughts. And so, when I looked into the disaster data, I was really surprised, and it's not going to be not a surprise to you, Bill, but I was surprised at how hazardous extreme precipitation and extreme tropical weather is. It's like it's the biggest, and it's not just the biggest here. It's, you go to India or China, you find similar huge impacts. And then of course the other surprise was, I wanted to in this book focus on the last 5 or 6 years, and in data set after data set, what I kept seeing was this big jump between like the early 2000s and the last 5 or 6 years. So the kind of rapidity of change was very striking.
Yeah, it is rather alarming, actually, when you look at that. And if that trend continues, a lot of people have to change fast. A lot of people I talk to are quite naturally confused about the understandings we have on climate change. What do you think would be the most important thing for us to get across to society about climate change?
Well, yeah, and I've tried to, I think, again, I think our conversations about the stalling versus the increased water vapor is a good one. I think it's important for us to communicate, the things that are the most straightforward and the most certain. And, I think there are things that are really complicated and difficult, and probably by the time we really understand how climate change influences them, it may be too late, but I think, I guess in a lot of ways, the motivation for writing this book, came out of conversations that I was having, both with international journalists and our local firefighting community here. And so, a couple of years ago, in December, I was standing 5 miles away from my house watching a fire burn very, very close, and wondering if everything was going to go to hell, while I was on the phone talking to a reporter from the National Geographic about drought in Africa and how, warming in the ocean and the air was intensifying droughts, and having these same conversations about how these relatively simple impacts of warmer air temperatures and warmer ocean temperatures, are making things more hazardous. And so I think, we don't want to dumb things down or be inaccurate, but I think it's also, a public service to talk about, the simple parts of climate change, and the fact that you're going to have, premium fuel in the tank, so that when, you hit the gas pedal, you're going to be going, 10% faster, and that 10% can make things more hazardous.
Alex, do you have any questions?
I've got a couple here. Let me go over to the Facebook page, and we've got a question there. It says, in regards to the Sahel activities, has there been an increase in the duration of Saharan dust exiting into the Atlantic Basin this year? Seems different than in previous seasons. So Did you see any of that in your research and in your data? Anything to do with the Saharan dust layer?
Oh wow, that's a great question, Alex. But I have to say that I have not looked at that. That when I'm looking at the Sahel, I'm worried about the Sahelians and kind of what's going on there in terms of famine prevention. So, sorry, I wish I could answer that question, but I would be making stuff up.
Next question would deal more in your expertise in drought. Since you are in California, was there anything that came up in the data that surprised you about where you're at?
Yeah, actually, and Bill, to come back to another question, you asked me kind of what did I learn that was surprising in the course of doing this book, and so it wasn't. So obviously, I live in California, and have been really impacted. Not me personally, but we're all very surrounded by these fires, and I had finished the book, but then Australia had an incredible fire year in 2019. And so my editor, Matt, asked me to add a chapter on that. And so, being a data guy, I went and grabbed the data and kind of worked out the math that linked increasing air temperatures to vapor pressure deficits to dead fuel moistures, and just kind of ran the numbers myself, and I was completely flabbergasted by how a degree or a degree and a half of warming can really decrease dead fuel moisture levels, setting the stage for explosive fires. So we put that in the book, and then in the Western U.S. in 2020, we've just had these incredible fire years. So, when I wrote the book, California had just had record-breaking years with like 1 million hectares burned. And then, in the last year and probably this year, we're going to have like 4 million acres of wildfire extent. So 4 times something that was already a record-breaking amount. And so, that link between warmer air temperatures and drier fuels is really robust, and it's wreaking havoc.
Well, that kind of ties in really well with one of the highlights, I think, in your book, where you say small changes can dramatically increase the chance of extremes. That's for drought. What are we looking at for flood in those small changes?
Yeah, I think, and this is, I think I would refer to a paper by Mark Risser and Michael Weiner, where they, looked at the flooding associated with Harvey, and, basically, attributed a fraction of the precipitation to climate change, and then, looked at how that impacted the flooding, and found a pretty big increase. And, it's of course, dead fuel moistures and fires are kind of easier than extreme flooding. But at least in that study, it really suggests that, that extra 10% can really trigger a tipping point. And, as your community knows, that can be really tricky. Is the levee going to hold? Is the levee going to break? But it's certainly, what we're seeing globally. And I guess that's something that, that I can kind of bring to this conversation, is that it's not just in the United States, right? We're seeing, these extreme flooding events, all over the world. Like there was just, there was one in Germany this summer, there was one in China, right? And so that extra tipping point, 10% more in certain cases, can be really, really bad, especially when that comes in a very short period of time, as we saw, in New York. So a little bit more, so you can take there's not like a global increase in precipitation. And in fact, you can show using energy balances that, we don't expect anything more than a 2% increase in global precipitation, say, due to climate change. It's very small. But when we look at these, most extreme precipitation events, we do see that they are increasing and they're having bigger impacts in a kind of nonlinear way.
All right, Bill, back to you.
Yeah, it's just coincidental, but that tends to be in retirement. My big interest has been the rainfall flooding aspect of hazards, mainly because I live in a place that's highly vulnerable to it. And I'm really starting to focus on the rainfall rate. And I'm not sure that that's complex. There's other things going on that may increase the rainfall rate that we're getting. In the Harvey floods, what I've looked at is that the bulk of the flood was driven by the first night of rain, which was less than a half of the 4-day storm total. But it fell in 3 or 4 hours, 20 inches of rain, 5 inches or so an hour. And then this year, Ida with the 3-inch an hour rainfall rates across the heavily developed Northeast corridor, where they probably build with less than their standard is probably less than 2 inches an hour for drainage purposes, because that's kind of what we use here, maybe less than 1. So it's these increased rates that we're starting to see, and I'd love to see more studies on that to see just how much we can project into the future. I have read one that suggested it probably won't increase that much more, but the frequency of those events may continue to increase.
Yeah, Bill, I was thinking of reaching out to you kind of later about, I'm talking with Stephanie Herring and American Meteorological Society, and we're talking with the American Association of Planners, and we're trying to get a dialogue going, like, are American planners aware of these sorts of risks, and can we kind of build better for the future? Because there's a lot we can do if we anticipate that this is going to be, a greater risk in the future.
Yeah, our track record hasn't been that good at it. We keep insisting on building the so-called 100-year event, and even without change, that was not acceptable. So with change, it gets worse. Yeah. I really enjoyed this discussion today, Chris. I look forward to reading your book and hopefully having you sign it when you come over here for the AMS meeting in early January.
That sounds fantastic. I'll look forward to it, Bill.
Okay.
I really appreciate the time to.
Mm-hmm.
All right, well, let's drop one more sponsor mention here, and then we'll close up the program. Great program today there, Chris. So today we want to remind everyone that we are helped to produce this program by USAA, South Padre Island, Texas Economic Development Corporation, Plylax Hurricane Clips, Maglite, and, of course, Blackmagic Design. They help us keep this program going and the National Tropical Weather Conference. Registration is open for the conference next year. We hope to do an in-person one, April 6th through the 9th at South Padre Island. Thanks so much for joining us today.